Hello everyone, I'm Kowshiq Kattamuri. So welcome to this very first video lecture of the series Introduction to Data Structures in C++. So in our today's video, we'll be learning about the concepts of STL, Standard Template Library. So in my screen, you can actually see to the right side, we have a notepad where I'll be annotating. And to the left side, we have a code compiler. So that is online GDB compiler. You can just go to the website that is already there in the description of our WhatsApp group. So you can set the language to C++ and start coding. So before we start, I would like to add some points to our course related to our course. So uh, why STL? So why are we starting with STL? So the main outcome of today's video is to help you people understand the data structures. So how do we use it? What are the data structures and how do we use it? And what are the functionalities do the data structures provide to us? All right. So these are the two main points. So what are the data structures? Like what type of data structures are available to us? And how do we use them? So we need to use them, right? So without knowing how to use them, so it doesn't make any sense to actually try to implement them or try to make frame some algorithm. And third one, so what are the functionalities does a particular data structure provide? So you'll not be using the same data structure to store all that sort of elements, right? So you'll be using some specific data structures according to the usage. So you must be able to identify. So for a particular case, for a particular problem, I'll be using a particular data structure. So you must be able to differentiate between them. So that is the main crux of today's video. So you'll be able to understand all these things. You'll be getting an overall overview of what are the data structures and how do we use them, and we'll not be going in depth like how do we implement it, how do we frame them. We'll be doing that separately, but as of now we'll be getting an overall overview of what how do we use them and what functionalities do they provide. So before starting, it's recommended that you please watch the video that I've sent yesterday. This announcement is for each and every one of you. So please go through the video that I've sent yesterday. That is, I've sent the link in the WhatsApp group. And for the people who have no idea of the basics of C++, they are highly required to complete the whole playlist, like whether it's Hindi or English, and then watch the yesterday's video and then start this video lecture. If you haven't done anything of them, like anything, like you haven't started the playlist and you haven't watched the video that I've sent, then please do not start this video. It will not be helpful to you in any case because you'll end up getting confused. All right. So I don't want that to happen with you. So let us start our today's lecture then. So that is STL. So what does it stand for? Standard Template Library. All right. So standard template library. So let us first see like how many data structures do we actually have. Okay. So starting with vectors, we have vectors, we have stacks, we have queues, we have maps, we have sets, and we have like in queues itself there is a further division. So like there is a DQ, there is a priority queue, and even stack we have some set of divisions as well, and in maps we have unordered maps, multi maps, and in sets we have unordered sets and we have multi set. All right, so we have these divisions as of now, and then in between stacks, vectors and stacks, we have something like list, and we also have I like these are all things like we don't need to focus a lot, like these doesn't are not in a lot of use as of now. To be honest, we rarely use them or we rarely encounter them, so I don't give a lot of priority to them, to be honest. So yeah, I just think these are the data structures that we have. So the main priority or the main importance that we need to give to is vectors, stacks, queues. DQ is also very rare, but still, in some sort of problems without DQ, you couldn't even solve them. Okay, so DQ, priority queues, maps, unordered set, multi-set is also, I don't think it is a very important data structure. And unordered maps, and same is the case with multi-maps. So that is also not, a very interesting or maybe very useful sort of data structure. So we'll start with vector. So before starting with the data structures, I'll even share the slides, and I've even made a Google document where you can find all the STL of each and every one. So I'll even explain you what is STL and all the stuff. So I've even made a Google Doc. I'll be sharing you at the end of the session, and also I'll be sharing a feedback form where you can give your feedback after going through the whole video lecture. All right. So it will be helpful for me to actually improvise myself and put my best out in the next video lectures, in the upcoming video lectures. So yeah, so let us first understand what do we mean by standard template library. Okay, so for example, there is a boy named Raj. All right, so there is a boy named Raj, and he is so interested in going through a lot of books and all, but he doesn't want to spend any sort of money. Okay, so he doesn't want to spend any sort of money. So what will he speak? What will the first decision of his would be? So he would actually try to prefer a library, right? So he would actually try to prefer a library. So he would definitely see library as an option to get all the books that he wanted. So similar is the case when actually trying to put something in your code. All right, I'm assuming that you all know the basics and all. So I'm actually trying to compile all the stuff without explaining what do include mean, what do using mean, and all the steps. Okay, so I'm assuming all this that you know all this things. So if I just write cn n, so if I just write this cn, so you know like what does cn actually mean. So cn means that take the input from the user. So if I don't mention what does n stands for, n stands for, all right. If I don't mention what does n stands for, so then compiler cannot understand what is he actually trying to say. So we must try to mention what n stands for. So I'll be mentioning n to be int n. And then if I just mention scene n, so I know that scene stands for to take the input, to take input. But how does a compiler know that scene stands for that? So it needs to refer to something, right? Compilers will be looking out for something. So that is known as the library. Alright, so it will be looking out for some library. Same as Raj looked out for a library to refer the sources that he wanted. Similar is the case, a compiler would like to refer the library. In the library, it will be seeing that scene stands for this, to take the input. So it does the same function. So it takes the input. So this is how it works. So when I say cin n and when I say cout n, all right. So I'll just run the code here. So take some time. Yeah. So if I just enter 3 and I press enter, so I got 3 actually. Yeah, 3 and I've got 3, right? So this is the output. So this is how it works. So you need to explicitly mention what is actually happening. So CNN and cout. How does the compiler know all these things? Just because of the library that we have included. So the library here is /include bits /std c++.h. All right, this is the library. Now you have understood what is the meaning of library. Okay. Now what does STL stand for? So before that, we'll go through the data structures once. Suppose same is the case. Let us assume we have Raj here, all right, and he wants to store the milk that is going to buy from a shop, nearby shop. So does he prefer use like a box like this, or does he consider a bottle to store the milk that is gonna buy? Fine. Does he store this? Like, does he use this box, or is he going to use a bottle? Of course he's going to use a bottle, right? He's not going to use a box to store the milk that he's going to buy. So he is able to understand, like he got a conclusion that he's going to use a bottle to use rather than a box to use, because the data, or the object that is storing is milk, and that is in a liquid form. So for that, it's preferred that we use a bottle so that you can later on consume it properly, easily. All right. So you'll be considering a bottle to store the milk. All right. So this is how he's able to differentiate between the structures that he has to store the data. So similar is the case. We have various data structures as mentioned above. vectors, stacks, queues, maps, sets, all this stuff. So we must able to understand to the particular case what sort of particular data structures I'm going to use. So it's not like I'll be using the same particular same data structure to store all type of elements and I'll be solving all sort of problems. No, that's not possible. So each and every data structure has some functionality associated with it. So you need to understand that for some type of problem or for some type of case, I'll be using that particular data structure to solve the problem. So that is very, very important. That is the differentiation. All right. So let us start with vectors now. Vectors. So coming to the concepts of vectors. So vector is known as a dynamic array. All right. So it is known as a dynamic array. So what do I mean by dynamic array? So generally we represent an array as int ar, and you take the elements 1, 2, 3, 4, 5. All right. So this is a general representation of an array. Suppose you would like to add an extra element, sixth element into it. So is that possible? No, because you are already exceeded the size of the array. Like your array size is defined as 5, and you're trying to exceed it by adding an extra element. So what is the process that you're gonna do here? You'll be taking a new array, add new, and you'll copy all these elements into this, and then you'll add the sixth element into this. All right. So this is how it's done. So in the case of conventional arrays, all right. But now, in the case of vectors, you need not do all those things because vectors resizes itself. All right, it adjusts, it resizes itself in such a manner that you can actually try to add elements as many as possible. So let us see that. First, we'll take the size of our vector from the user. So let us represent it by n. So int n, we'll be taking it from the user. So c in n, and now we'll represent the vector int vec of n. Okay, so let us understand what is this in great detail. Vector int vec of n. Okay, so this describes that I'm asking my vector to store elements that are of type int. Okay, so I'm asking a vector, the vector that is right now with us. The name of the vector is vec. This is the name. Okay. So you can even store it as, you can even name it as some other thing. It's up to you. You can name it as you want. So I've named it as vec. So I'm asking my vector to store the elements that are of type int. All right. And now this n indicates the size. Okay. I want my size of the vector to be initially to be n. All right. So this is how you can represent. And now for int I equal to 0, I less than n, I plus plus, you can start taking the input from the users. So C in vector. So it's not like it plots at random. So I'm asking my user completely to give the inputs that he wanted. So that is the reason I've made a for loop and I'm asking the user to give me the inputs. So vec I. So it starts from I starts from 0. So my vector is like this. All right. My vector is like this. So this is 0, 1, 2, 3, 4. Total 5 size. Like if I represent n to be 5, so this is a 5 size vector. So I'll be taking the input from the user. Vec of 0, vec of 1, vec of 2, vec of 3, vec of 4. So we are done. Now, if I wanted to add some extra element to it, so what will I do? I'll be doing like vector pushback of the element that I wanted to add. Let us assume I wanted to add 50. So what does this pushback represent? Pushback means that, so I'll be writing it here. Pushback. So pushback actually asks vector to push an element into it from the back. All right. From the right end, or you can even assume like this. So you can add an extra element here. All right, you can ask the vector to add an extra element by adding the by using the STL pushback of 50. So I can even add an extra element to this. I will even ask my vector to add pushback of 60. All right. So now initially we had five sized vector. So I'm assuming my n to be 5 here. All right, my n to be 5. So I have a five sized vector, and now I have asked it to push back two elements. So now the n should be 7, right? The size of the vector should be 7. So how can we check that the size of the vector is 7 or not? Just see out vec dot size dot ended. Okay. So what does this dot size represent? So I'm explaining each and every STL related to a vector, like in the process, like I'm writing it in the code as well as showing it to you over here. So size dot size. What does that give you? It gives you the size of the vector. It gives you the size of the vector. So now it must give me the size of the vector as 7. And also to I also need to check what are the elements that are there in my vector. So if our int I is equal to 0, I less than vec dot size. All right. So vec dot size I plus plus. I'll be showing the output each and every element of the vector. So ended. All right. Ended. So let us run the program and check. It's taking some time. So first I'll initialize my vector with n equal to 5, and then I'll give the elements 1, 2, 3, 4, 5. So let us see. Yeah. So you can see that the answer is 1, 2, 3, 4, 5, and then 50 and then 60. All right. So we have got all our vectors and even the size reflected as 7. So you can see that the vector already resized itself. So we have initialized our vector to be 5, but it has resized itself to n equal to 7. So this is how a vector works. So you can easily understand that your vector doesn't actually depend upon the size. All right, you can do whatever you want. You can add as many elements as you want. Vector resizes itself. All right, resizes itself accordingly. So you need not worry about it. So this is a very good advantage of using a vector. So on top of it, we have some of the STL that we need to discuss in the case of vectors. Let us see them one by one. Just a minute. So we are done with pushback. We are done with size and all. So let us now see another STL. So this comes under the topic iterators. All right. So this comes under the topic iterators. Very, very important concept, guys. Like it actually simplifies a lot of process. So for example, let us take another example, Raj. All right. So let us assume he is a delivery person right now and he wants to deliver something, some object. So he needs to deliver this to Nagesh. All right. He needs to deliver this to Nagesh, but he exactly doesn't know the address of Nagesh. Okay, he doesn't know the address of Nagesh, but he knows that the exact apartment where Nagesh lives is four apartments away from Srinivas apartment. Okay, Srinivas apartment. So he knows the Srinivas apartment. Where Srinivas is a person where he lives, he knows his apartment, and he also knows that Nagesh apartment is four apartments away from the Srinivas apartment. So let us assume this is Srinivas apartment, and this is Nagesh apartment, and this is four apartments after. Okay, four apartments there. So what will he do? He'll first try to locate where is this apartment, right? He'll first try to locate this, and then he'll be going forward, right? He'll be going four apartments away from this point. So one, two, three, four, and then he's going to come up here. So he's like first trying to locate the reference point. So his reference point is Srinivas apartment. So he's trying to first locate it and then is iterating from there. He's moving from that point. So the same thing iterators does. For example, uh, now I have a vector. So this is my vector. All right. So the first element in it is 30, and then 45, and then 50, and then 75, and then 80, and then 90. All right. I wanted to know the exact position or exact address, or you might say the index where 50 is. All right. I wanted to know where 50 is. I wanted to locate 50. So for that, I'll be first trying to locate where is 30 is, right? So I'll be trying to first locate where is 30, and from there I'll be going one step ahead, I'll be getting 45, and then I'll be going one step ahead, I'll be getting 50. So first I need to know this address, right? If I don't know this address, 30 address, I cannot know 45's address, 50 address, 75 address, 80 address, 90 address. The reason being, in the vectors, all the elements are stored continuously. To the next of 45, we have, to the next of 30, we have 45. To the next of 45, we have 50. To the next of 50, we have 75. To the next of 75, we have 80. To the next of 80, we have 90. All these are stored in the continuous memory blocks. All right, all these are stored there. So you need to know the address of 30. If you don't know the address of 30, you cannot redirect to 50. That is as simple as that. So first you need to know this address and then move two steps ahead to get the address of 50. So how do we do it? So we'll be using an iterator. So how do we represent an iterator? So in this case, we are using an iterator for a vector. So we represent it as vector int semicolon and then iterator it. All right. So this I am pointing it to vec dot begin. So what does vec dot begin? So we have come across a new STL dot begin. So dot begin. So what does this give? This gives the address of the starting element of the vector. It gives the starting address of the starting element of the vector. In this vector, the starting element is 30 and dot begin gives that address. Okay, gives that address. And now your iterator it is actually pointing to this address. Your iterator is actually pointing to that address. Your iterator it is actually locating that address. So now you need to go two steps ahead to find the second element. So I'll be doing it plus plus, so that will be coming to 45, and then it plus plus, so that I'll be coming to 50, and now I'll be doing the C out star it. Okay, star it ended. So what does star it means, like do, like star it, the functionality? So star represents that it is actually address, right? It is an address. It is an address, that we have got a clarity. Now star represents that at that particular address, what is that element that is there? We are pointing that, we are storing that. All right. So star it actually points to the element that is present at the address in it. All right. So your it actually has the address, and in that address we have an element, and that can be accessed by star it. This is the main usage. So now we have our vector. So initially, what is the vector that we have considered? So the vector that we have considered is of now 7 size, because now initially it is of 5 size, and then we have added 50 and 60. So initially it is 1, 2, 3, 4, 5, and then we have added 67, and now my it is actually pointing to it over here. Now I did it plus plus, so it points to here, and again I did it plus plus, it points to here. So my output must be 3. And why did I do 2 times it plus plus? I could have done it plus equal to 2 or it equal to it plus 2, because your iterator cannot work like that. Your iterator can only move once to the right. Okay, you can add only once. You can only move at once. So I've done for twice. So my iterator must point to this. Now star it must give the value as 3, because at this address 3 is stored. So I must have the output as 3. So let us check it. I'll run the program again. Yeah. So the n is 5, and the input that I'm trying to give is 1, 2, 3, 4, 5, and yes. So I hope you understood. So first we have got the size, that is 7, because we have added 50 and 60 and 70, so the size got updated to 7, and the elements are 1, 2, 3, 4, 5, 50 and 60, and then we have also mentioned C of star it. So star it is actually pointing to 3, so star it gives the value as 3. So I hope you understood, like, what does iterator do. So this is how you can actually try to get all the elements. So even here, you can take this, or I can remove all these things. So you can even try to output the elements using iterators. So for vector int iterator, so it's very, very important that you are mentioning your iterator type. Here we are using vector int So I'm mentioning my iterator IT to be of vector int. If you are using some character, you need to mention that character. All right. So IT is equal to vec dot begin and IT not equal to vec dot end. Okay. So I'll be just moving the screen here. Vec dot end. So what do I mean by vec dot end? This is the stopping condition. So vec dot end. So dot end. Dot end. So dot end represents the address. It gives the address of the next element of the end of the vector. Okay, end of the vector. So in this vector, the last element is this, right? 70 is the last element, and the next to it, the space that we have, this address is nothing but vec dot end. All right. So I must not access this because that is outside of my vector. My vector must be confined to only this 70. I must not access this. So I mentioned the stopping condition to be it not equal to vec dot end. So I must not access the element that is there after my vector. I shouldn't bother about it because that is not included in my vector. So that is the end. So remember, vec dot end doesn't point out to the last element of the vector. Rather, it points out to the next element of the last element of the vector. So I shouldn't need it. All right. So that is the reason I kept it not equal to and moving your iterator plus plus. Okay. And so I'll be seeing putting out star it, okay, star it and then. So you must get all the elements that we are storing in the vector. So let us run this. So first n is equal to 5. That is a vector size that we are declaring. And now we are pushing the elements 1, 2, 3, 4, 5. So we have got the elements, right? So first we have shown the output as vector size, that is 7. And for vector int iterator, starting from beginning, all right, starting from beginning, moving iterator once and once, we are getting all the elements that have actually been stored in the vector. So 1, 2, 3, 4, 5, and 50 and 60. All right. So this is 50 that we have stored. This is 60 that we have stored. I hope you got it. So this is how iterator works. So this is as simple as that. So star 80 denotes that at that particular address, what is the element that is present? Just output that. Okay, that is what it is showing actually. And for each and everything, you need not mention this. So vector int type, you are mentioning vector int semicolon iterator it. Now, if I take vector character, again, I need to mention it explicitly. So you need not do all those things. Rather, you can just replace this as auto it. All right, auto. So auto it equal to vec dot begin. So what does this auto mean? Auto mean? So I hope you have understood how are we trying to learn. So we are experimenting. We are trying to put that in the code and then simultaneously learning what does that actually mean. So auto in the sense it remodifies. Sorry, uh, it modifies itself according to the input. All right. So now your vector begin is something is an address. All right. Your vector begin is an address. It is a 6 digit something. It will be a very big thing. It's an address. It has a lot of characters. It has a lot of numbers. All this stuff. So an iterator is the right data structure to. I mean, iterator is a right data type to store it. All right. Iterator is a correct data type to store the addresses. All right, store the addresses. So your IT must be an iterator, but without mentioning it, you're just putting it as auto. So your auto in the C++ automatically, okay, automatically modifies itself as, automatically sees itself as an iterator because you're equating it to vec.begin. So when you're actually equating it to vec.begin, your IT understood that it is a sort of address. So I'll be modifying myself as a carrier for an address. So what would be a carrier for an address? It would be an iterator. So iterator is the right data type to handle the address. So your IT will remodify itself. Your IT will cast itself as an iterator. So is it begins from vec dot begin, it dot vec dot equal to end, it plus plus. This is how it's done. You can even use this auto. All right, in a similar manner. So let us remove all these things. So auto I equal to 0, I less than vec dot size, I plus plus, and C out vec of I. The same thing happens. You'll be getting all the elements because now your auto I equal to 0. You're equating I to be 0. So your I will understand that now I need to be a int to carry this integer. So let us put n to be 5 and store the elements 1, 2, 3, 4, 5. And yes, so we have got the elements vec size to be 7 and the elements to be 1, 2, 3, 4, 5, 50 and 60. All right, so this is how it works. So you have understood what do you mean by pushback, what do you mean by size, what do we mean by auto, iterators, all this stuff, like very very important stuff, guys. So this is a where you need to have an important understanding of how to use the vectors. So this is how it's very very easy, nothing much complicated in this. You just need to know how are we actually trying to iterate the vector. All right, so we have got this. And another representation of vector could be vector n comma 0. What do I mean by vector n comma 0? In the sense, I am declaring a vector, I am declaring a vector of size n, and I'm putting all the elements to be 0. Okay, and putting all the elements to be 0. I'm declaring all the elements in the vector to be 0 at once. So let us do this. So for verification purpose, vector int vec n of 0. So I'll be showing the output int I is equal to 0, I less than n, I plus plus, C out vec of I, and then so let us run this. So put n to be some 5 and see 5 zeros 1 2 3 4 5. All right, so we have declared our vector vec to be of n size and have all the elements in that vector to be 0. So you can declare your vector in this fashion. So these are different types of representing a vector and all the stuff. We have seen the iterators, we have seen the auto, and there are some other STL as well. So I'll be showing you the last type here. Instead of for int I equal to 0, I less than an I plus plus and all the stuff, you can write this as like this is a short hand technique for auto I belonging to vec C out I end. So what does this mean? So we shall go in detail for auto I in vec C out I end. What does this mean? Auto, again, the same thing. So you're telling I to remodify its data type accordingly to the elements that are present in the vec. For example, if my vec is of character, then my I would have been the character. Auto will tell I to be a character data type now. Now your vec is of int. Your vector is your vector int vec, right? So your vec is of int type. So your I would be automatically putting itself as an int data type carrier, and then you'll be putting all the elements like out C out I end. So you're directly accessing the elements in the vector. It's not like you're going to the index. So in the for loop that we are conventional for loop, your I represents the index. Now you're representing the direct element itself. So if this is the vector that we are considering, 1, 2, 3, 4, 5. So my I would be 1, I would be 2 year, I would be 3 year, I would be 4 year, I would be 5 year. All right. So your I is directly directly taking the element that is there in the vector. All right. So let us see now. So we have declared all the elements to be in the vector to be 0. Now let us put 100. Okay. So now let us run this. So my n would be 5 and we have got 500s, right? See out high. So all the elements are 100. So that is the reason we have got the output to be 500. I hope you got it. So this is a shorthand technique of writing a for loop instead of writing it in a conventional form. So I hope you got it. So you're right. Now if I can just make it as long and ask the vector to carry some very big elements, your I will be automatically taking that role. Your I will be taking the long roll and it will be storing the elements. So I'll be running it and I'll be giving the n to be 5 and you have got the answer, right? So I can even change this. Like let us take character array and let us put all the characters to be A and now run this. We just need to give the input as the size. Okay, I'm giving 6 n equal to 6. We'll be getting 5 A's. See, sorry, 6 A's. 1, 2, 3, 4, 5, 6. So your I has taken the role of a character data type. So your I is directly taking the value of the elements that are present in the web. So this is how it goes on. So we are done with for like shorthand technique for, and we have seen auto and iterator. Iterator is a very important concept, guys. So if you don't understand iterator, it will be very difficult for you to go through the data structures in the later on stage. Like you can actually simplify a lot of things using iterators, directly pointing to that elements and all the stuff. All right. Now there's another important factor here. So another important data type, that is pair. Okay. So let me remove this pair. So what is pair? So like pairs are like pair in the sense, as the name says, two. All right, pair in the sense two. You're trying to hold two elements at once. So if I wanted to hold 3 and 5, all right. If I wanted to hold 3 and 5, there is an element 3, there is an element 5. So what would I represent? Pair int is equal to 3 5. All right, so this is how I represent. So pair int, I must also name it. All right, so pair int p, so this is the name of my pair, and that is holding 3 comma 5. So your pair is such a data type that it can hold two integers. Now you can even make it further, like pair int int and end and name it something like P. All right. So in this is a data structure, like this is a data type where you are holding at one pair as well as an integer. So you can totally hold three integers here. All right. So this is how it works. So you can just go on. You can represent this int as parent, and then it goes to four elements. You can hold four elements, and then again you can put instead of this int another parent. So now you can hold five elements. So it's up to you. You can go on doing how many elements you want. So that is a different scenario. So let us use that here. All right. So I'll declare my vector to be a pair type. Pair int vec. All right. Pair in, and that I'll be having n size. So I'll be taking the user's input for int I equal to 0, I less than n, I plus plus. I'll be taking c in vec of I dot first, vec of I dot second. So what do I mean by vec of I dot first, vec of that by second? So here, let us see here. Dot first, dot second. So dot first in the sense, in the pair, the first element in the pair. Okay, the first element in the pair. Second, the second element in the pair. The second element in the pair. All right. So this is the vec dot first, vec dot second. But why am I writing vec dot first? Because my vector vec, my vector vec, my vector vec is of pair int comma int type. That means in my vector, like this is a vector. Let us assume n to be 5. All right. So 5 size. Each of this block has a pair. Okay, pair int comma int. This also has pair int comma int. This also same. So each and every block of your vector has the data type in the form of pair int comma int. So your vec of I in the sense, like starting from I equal to 0, vec of 0. What does vec of 0 represent? This is the first block that is representing. So that is acting as a pair of int comma int. Now to get the first element, I'll be putting dot first. So dot first in the sense, this is what I'm trying to get. Dot second, this is what I'm trying to get. Dot second, this is what I'm trying to get. All right. So after that, so for each and every block, there are n blocks. So we have done the for loop for n. For int I equal to 0, I less than n, I plus plus, C out, vec of I dot first, and we'll be having a gap dot vec of I dot second and end. All right. So end gives us space, like it goes to the next line. So let us now run the program. Okay. Uh, we'll take n to be 5. So my first input will be 1 comma 2. My second input will be 2 comma 3. My third input will be 4 comma 5. My fourth input will be 6 comma 7. My fifth input would be 8 comma 9. And this is how your vector shows. So 1, 2, 2, 3, 4, 5, 6, 7, 8, 9. So your vector has given you all the values that you have stored in the form of pair. All right. So you can even see the size of the vector. See of vector size, you'll be getting the vec dot size to be 5 because there are 5 blocks, right? It's not like how many elements you're storing, rather how many blocks of address it is your vector has. So it is of 5 size, right? 5. So you'll be having the answer as 5. In the vector 5 size vector, each block is holding 2 elements. So in total 10 elements. That is not the answer that you'll be getting through dot size. Dot size gives you the vector size. Your vector size is 5, and this is what your vector will give. The vec dot size will give you as the answer. I hope you are getting it. So this is a brief overview of how do we use vectors. I don't think I've missed anything. I've shown you all the type of things. Instead of pushback, we can use m plus back. So pushback is what we are doing, right? So you have seen what's the function of pushback. Instead of pushback, we can use m plus back. All right, m plus back. This is also similar to pushback. Just thing is, m plus back runs faster. Like it gives you to access, like make your program run faster than pushback. This is what like it's known. So nothing much difference. You can use any of them. Either of them you can use it. So we are done with pushing the elements. We are done with getting like going through the vector through address navigation. We have seen the short hand version of for loop, and we have even seen the insert, like how do we push the elements into it. We have seen the size, we have seen the pair type. So this is all for a vector that we have need. So other things are also there, like erasing the element and popping back the element, copying a vector from one vector into another vector. All these things are there. I've configured all this them in a document. I've put all them in a document, all of them in a document. I'll be sharing the document to you. You can refer to it. All the links are there over there. You can just redirect to the link that you wanted to refer, and you can see, you can learn a lot of things from there. I don't need to explicitly explain all of them. These are the main points. These are the main fundas that you need to remember. Like how do you iterate through a vector? What is a vector? How do you use it? How does it function? How does it work? These are the things that are very, very important to learn. And I've made sure I covered all those things. And pair is also an important thing. And I've explained you very clearly how to get an access to the pair. How do you represent the pair? So try to frame the code on your own. Write all these things. Try playing with a lot of inputs, and you can easily understand from them. So we are done with vectors. We'll start with queues. We'll start with stacks now. So starting with the concepts of stack. Stack. So what do we mean by stack? So it is also known as last in, first out data structure. Okay, last in, first out data structure. So let us represent the stack like this. Even general, usage, we use like general daily life, we use this term stack of books, or maybe stack of items that are placed there. So what do we mean by stack of items, or stack of books, or stack of objects? Like one is placed above the other. Okay, so this in this fashion. All right. So one is placed above the other. Here it is a closed end. Here it is a closed end. Here it is an open end. All right. So you are able to place the objects one over the other, and this is the first one that might have been entered, right? This is not the first one that might have been entered. This is the first one that should have entered, and on top of that we are putting this, and on top of that we are putting this, and this, and this, and this, and this goes on. So the first one, the last in first out, means this is the last object that we have kept in this stack, and that will be the first one to be out if I wanted to empty this stack, right? So if I wanted to empty this stack, the first object that I need to take out of the stack is this, right? This is the one that I need to take it out, and this is the last one that to get into this stack. So that is the reason we named it as last in first out data structure. So if you want your data to be stored in this fashion, like uh, to access the last element that have been entered into your data structure to be the first one to be accessed, then you can store the elements in this fashion. So there are some terminologies again here. So let us first declare a stack and then go start learning all the stuff. So stack int s is what I'm declaring. So again, so what is the type of data that is holding, that the stack is holding, that we need to clearly mention, that we are mentioning it here, stack int, and I've named my stack to be s. So how do you push some elements into it? S dot push of, so I'm assuming that I'll be pushing 10. So what does push mean? Uh, so push dot push. So push means that if I assume this is my stack, so if this is an empty, let us assume this is an empty. Now I'm trying to push 10 into it. So if I say s dot push 10, so my 10 goes up here. And if I say s dot push of 20, now my 20 goes up here. And now if I say s dot push of 30, my 30 goes over here. All right. So it goes on. So your stack is actually trying to take the input with the STL push with using this command dot push. So s dot push is done. I'll be pushing now 20, s dot push 20, 30, s dot push of 50. All right. So I pushed three elements, right? Now I wanted to access the top element. I wanted to access the top element. Right now, there are three elements itself, so I can understand the top element would be 50 because that is the last element that I've pushed in. But suppose there are n number of elements, like there are thousand and lakhs, something like that, and you don't even know what is the top element that is there because you are not the user there. So to access that, I can take one int a and I'll be using it to store s dot top. So what does top mean? So top. So this indicates this gives you the top element of the stack, or top element of the stack. So my top element must be 50, 10, 30, 50. So my stack is in this fashion, right? So first I've entered 10, and then I've entered 30, and then I've entered 50. So my top element must be A. Like A must be equal to 50. So A will be storing this 50. Now I wanted to access 30. So for that, for accessing 30, I need to remove this 50. Without that, I cannot access this. This is not a vector, no. So vec of 0, I can get the 0th element. Vec of 1, I can get the first, like after that, after 0, what is there? I can get it through vec of 1. This is in the case of vectors. But here it is stacks. In a stack, you need to clear up the elements that are there on top of it to access that particular element. I wanted to access 30, and for that reason, I need to clear up all the elements that are there on top of it. So how do I clear it? There is some terminology again. That is s dot pop. Okay, s dot pop. So what does this pop do? Dot pop. This removes or deletes the topmost element of the stack. All right. So deletes or removes the topmost element of the stack. So s dot pop, that is a function of pop, and we have seen the function of the top. And let us now see the size of the stack. So first we'll see out the things that are there. So we'll see out a and endl, okay, and we'll even see the size. See out s dot size. So dot size similarly. All right, dot size gives you the dot size gives you the size of the vector, sorry, size of the stack. All right, the number of elements that it is actually holding right now. First we have stored 10, then 30, then 50, then we have stored the top element, that is 50, into a, and then we have popped out. After popping out, this must be gone, like 50 must be deleted. So after popping up, we will see what is the topmost element that is there. S dot top, and then so the topmost element now must be 30, right? Because we have deleted 50. and we'll even see out A must be 50, and the size that must be 2. Let us verify now. So we have run the program, we can see yet. So S dot top is 30 because we have popped out, and in A we have stored the S dot top, that is 50, and we have got the size to be 2 because 50 has been deleted. Only 2 elements are left. So that is S dot size. So I hope you understood how do we actually go through the stack. So this is how you access the elements, the topmost elements itself you can access. If you wanted to access the elements that are inside the stack, you need to keep popping them, you need to keep popping the elements till you access till you get the access of an element that you wanted. This is not like a vector, like you can directly access through the help of index. That's not possible here. To get an access of the element, that element must be on the top of the stack. All right, so this is all about stack. There are a lot of other STL related to stack as well, empty, swap, and lot of things. So I I've kept all of those in the document. Just refer to the document. You can learn all those things from there. Now the next data structure would be queue. Now coming to the concepts of queues. Okay, so queues. So how do we represent this? We can represent this in this fashion. All right. So queues. So the only difference between a stack and a queue is, in stack you find this to be closed, you find this to be open. But in queue, both are open. All right. Both are open. You can access the elements even from the down or even from the bottom, or we would say even from the front, even from the back. All right. So the same usage is also seen here. I mean, the same functionality, it's almost the same, but you can get an additional access to the elements that are from the uh, the front side as well as the back side. For example, if I push 10, so 10 goes to here. Now I push 20, 20 goes here. Now I push 30, 30 goes here. Now I push 40, 40 goes here. Now I push 50, 50 goes here. All right. Now, if I wanted to access the front element, this is the front element. All right. This is the front element. This is the back element. This is the back element. So you can front this, you can take the access of this, you can take the access of this. So let us see this. So Q and Q. Similarly, the way that we have written for stack, you need to mention that in the data type that your stack is that your queue is holding. So Q int mentions that your queue is actually holding the data which is of int data type, and I have named the queue to be Q. All right, or let us name it to be some cow. Okay, now cow dot push of 10, cow dot push of 20, cow dot push of 30, cow dot push of 40, cow dot push of 50. All right. So we have pushed this 5 elements. Now I wanted to get the access to this element. All right. I wanted to get the access to this element. So what will I do? I'll be doing the like I'll be storing it first. So I'll be storing it in A. So int A is equal to cow dot front. So my int A must be 10. All right. Int A must be 10. This is A. Now I want to store 50. That is the back element. So that for int B is equal to cow dot back. So we have seen two STLs here. So one is dot front. So which gives the access to the front element of the queue, and dot back gives the access to the back element of the queue. All right. So let us see this first. Let us run this program. Let us take the outputs as A and B. C A space B, and yeah. So let us run this program. Uh, so yeah, so we have got A to be the front element, that is this. We have got A to be 10 successfully, and B to be cow dot back, that is the last element that we have pushed into the queue. So B is 50. All right. So we have got that required. Now I wanted similar to stack, to access any element in the queue, you need to pop out the elements that are on top of it. For example, if I need to access 30 here, I need to pop this out, I need to pop this out. But in a stack, but here it acts in the opposite manner. Like if you pop out, this is the one that's gonna pop out. this is the one that's going to pop up next, and then you can get the access to the 30. So that is the reason queue is also known as first in, first out, FIFO, like first in, first out. So I had actually pushed this 10 first, and then 20, and then 30, and then 40, and then 50. Now, when I pop the element, when I do pop, I'll be able to get the element, I'll be getting the access to this, like I'll be deleting this element, and then again pop deletes this element, and then I can get the access to this 30. So if I do cow.pop, and okay, cow.pop, and again if I do cow.pop, uh, and now if I see out cow.top, okay, now if I see out cow.top, I must get 30 because I have popped out 10, I have popped out 20, now I need to get 30. So let us run this program. Uh, okay, okay, so this is not top, this is front. So yeah, we have only two terms here, front and back. All right, so please don't confuse, like I confused here. So cow dot front. So 10, 50, and yeah, you can just put end here so that we don't end up in confusion. Uh, so yeah, 10, 50, and cow dot front 30 because we have popped these two elements out, and we have got front element that is 30. So this is how you can access the elements. So the thing is, in the stack, for accessing any element, you need to come from top to bottom. Here, you need to go from bottom to top. Or in other words, you can just remember this. It's a FIFO. Q is a FIFO. That is first in, first out. So whatever you have pushed in first, that must be the element that will be coming out. So what you have pushed first will be in the front end. Okay, so you will be taking it out. So this is the front, and when you're popping it, when you're popping your queue, these elements gonna come out first, and then you can go to the top of the queue. So you can just remember in that fashion. So this is all for queue. There's another set of queue is also known DQ. So where you can actually access that element from either side. Like you can even delete the element from this side. Here in queue, we are only able to delete the elements from this side, right? So in DQ, you can even delete the elements from the either side. So I'm leaving it as a task to you. Like you can go through it. I've put every STL record related to that in the document. You can just go through it. So this is for queue. And now let us discuss the next section, that is priority queue. Okay, priority queue. Uh, Priority queue. So what does a priority queue do? This is a very interesting. This is a very interesting data structure. So this is also a queue. Okay, so this is also a queue. Now if I assume I push 30 first, and then 70, and then 10, and then 60, and then 100, and then 50. Okay, I've pushed all this, but internally, the priority queue doesn't store the elements like this. It stores in this fashion. The maximum element would be at the top. So 100, and then 70, and then 60, and then 30, and then 50, and then 10. This is how your priority queue stores. Like as soon as you add any element, it rearranges itself. The data inside it rearranges it such a way that the top element means the order of the elements would be in a decreasing order. All right, decreasing order. So that is the reason it is also generally known as maxi. Okay, maxi. And if you wanted to make sure, if you wanted to make in such a way that your minimum element comes at the top, you can have it to be min heap. Okay, min heap. So this is how it is. So you can rearrange your priority queue in you can rearrange your priority queue into min heap using some other STL. We'll see that later. But now priority queue is like such a data structure where you can rearrange your elements. The priority queue itself rearranges its elements in such a manner that all the elements will be in a decreasing order. So let us see that. So we'll first declare the priority queue int pq. Okay. Now I'll push the elements pq dot push. So same is the case that we have taken the example pq dot 30, pq dot push of 70, pq dot push of 10, pq dot push of 60, pq dot push of 100, pq dot push of 50. All right. So Now the top element would be, so let us store that int a is equal to pq dot top. Okay, and we will even pop that. We'll pop it. So pq, the same, you can do that pq dot pop. So pop in the sense deleting it. All right, we have already seen that. And now let us see out the a and see what is the top element that we are getting. So 100. So as I said, so your priority queue rearranges its element in such a manner that your top element will be A. And when you're actually popping it out, your 100 is no more at the top. You will be getting 50. So let us check 70. So let us check that. So space and then pq dot top now and end it. So now it must give you 70, 100 and 70. So yes. So your A is 100, that is PQ dot top, and then your other element, that is PQ dot top. Because after 100, we have got the, after pushing all these elements, we have popped it in the 13th state, 13th line. We have popped it. So your 100 is no more in the queue. So the top element that is next, it is next after that, it is 70. So that is what we have got. So this is how you can go through priority queue. So you could have understood the importance of priority queue by now. So you can have your elements in arranged in such a manner that you can get the maximum element on the top, like it arranges in the decreasing order. Now, if you want to be what this to be in an like increasing order, like the minimum element must be at the top. So you can write this vector int greater int. So this is how you'll be mentioning your priority queue. Priority queue int vector int greater int. So don't bother, don't try to dig more into what does that mean, and don't do all those things. Just understand how are we dealing with the things. That's it. So you can just remember this STL just like this. And now if you see, your A would be PQ to up top, and that would be the least element. That is 10. Okay. And then when you pop it out, 10 will be gone, and the PQ top would be 50. So let us see that. So 10 and 50 as set. Because now your priority queue is acting like a min heap. Okay, it's no more a max heap. So if you want your priority queue to act as a max heap, you need not declare this whole stuff. Okay, so you can just remove it. If you wanted to act it as a min heap, you need to put the stuff, and your priority queue will act like the minimum heap, and then it will be showing the minimum element on the top of the queue. All right. So I hope you got it. So this is all for queues, like a general queue and a priority queue. Next, we'll start with the sets. Come to the concepts of sets. So sets is known for two functionalities. One, does not maintain duplicates. Okay, does not maintain duplicates. Second, maintains the decreasing order, or you might say increasing order. Yeah, increasing sounds well. Maintains the increasing order. So what do I mean by that? Similarly, what we have seen in the priority queue, like in priority queue, your elements piles up in such a manner that in a general priority queue, not the min heap, the max heap that I'm talking about. So your top element would be the maximum of all the elements that you have pushed in. In the sets, the similar fashion, when you're pushing in all the elements into the set, when you're trying to insert all the elements that you want to into a set, the set rearranges itself in an increasing order in this manner. Like this element here would be greater than this, and your increasing order would be in this manner from low to high. Okay, lesser value to a higher value. So it goes on in this fashion, and it does not maintain duplicates. For example, if you go on inserting ones for 5 times, okay, if I go on inserting one for 5 times in the set, only one will be stored. Okay, only if I go on inserting 10 twos, and in the set only one two will be stored. So let us see that. So set int s, so it's the same declaration. My set int means that I'm declaring a set of int data type, and the name of the set is s. And now I'm inserting the elements s dot insert of 10, s dot insert of 10. So let me copy this statement for two more times. And now I'm inserting print 30, and now I'm inserting 30 again, and now I'm inserting 30 again, and now I'm inserting 50, and now I'm inserting 50 again. Okay, so I've inserted 10 for 4 times, 30 for 3 times. So 10 for 4 times, 30 for 3 times, and 50 for 2 times. All right. And let me insert and in different order. Let me insert 70. Okay, I've inserted 70 and I've inserted 70 again. I've inserted 70 again, and now I'll insert 5. Okay, I'll insert 5. I've inserted 5 again. So 70 for thrice and 5 for 2. Okay, 5 for twice. Now let us see what are the elements that are there in the set. Let us get the elements out of it. So how can we access the elements that are there in the set? So for auto IT, okay, so auto IT, as you have learned this concept of auto IT, s dot begin, similar is the case, till IT not equal to s dot end. Okay, s dot end, IT plus plus. So now I'm putting out cout star of IT. Okay, star IT, and I'll be putting end in. So I'll be getting all the elements that are there in the set. So I must get the output to be 5, 10, 30, 70. For the reason B, it maintains in the increasing order. So this is the increasing order. And yeah, missed it, 50 and 70. All right. So 5, 10, 30, 50, and 70. And it does not maintain duplicates. So even though I've kept, like I pushed 5 for twice, I'll be only having one 5 in my set. So let us see that. Uh, okay. So yeah, I did a mistake in the for loop. Fine. Now let us run it. So you can see that 5, 10, 30, 50, 70. All right. So we have got 5, 10, 30, 50, 70 in the same fashion. It doesn't matter how many times you have tried to insert an element. It will only insert for once. Okay. So that is the most important character of a set. And also it maintains the increasing order. That is also an important function of a set. Now, what are the other functionalities that can be seen? So after doing all these things, I can even find like let me see. I wanted to check if I had an element. If I had 80 in my set. So how can I find that? I can see s dot. So let me see. Auto it is equal to s dot find of 80. So this is what I meant. Like I wanted to check if I had the element 80 in my s. If I don't have the element 80 in my s, in my set s, this it will point out to the s dot n. So if my it point outs to s dot n, I will say that cout not there. Okay, and end it. If it is there, I can just say that else cout there. All right. So I actually trying to find the address that is there. If 80 is there, then I could get some address. And if that address is not equal to end s dot n, that means it has not gone out of the set. It has not got out of the set. All right. If it is not equal to n l means it has not gone out of the set. So that means there is 80 in the set. I'll be cout. I'll be putting the output as there. If it is not there, that means the IT that I've got is actually pointing out to the end of the set. That is equal to end. All right. So let us run it, and you can see not there because our IT is actually pointing out to s dot n. That is the end. The like if I assume this is the set, all right, it is pointing out here. So that is the reason. So we have understood how can we use the dot find. All right, dot find. And another STL in this is we can even use arrays or STL. I have kept that in the document. You can go through it, and you can even see count. So if I say cout s dot count, s dot count in L, okay, s dot count, I'll be getting the size of my set. Okay, I did a small mistake. S dot count. uh, where am I missing? I don't think it is count. I think Let us try with size. Yeah, S dot size is 5. So like yeah, sometimes we miss this STL, we confuse a lot. So size gives the size of the set, size of the set, S dot size. So S dot size gives the size of the set. So these are some of the STL related to a set. So I hope you got some clarity, like what are we trying to do using the set. So the main functionality here, it doesn't maintain any duplicates and it maintains the increasing order. The other two important segments of a set is lower bound and upper bound. Okay, so lower bound and then upper bound. So what does lower bound and upper bound denote? So if I say S dot lower bound of 30, if I say S dot lower bound of 30, or let us say 35, okay, let us say 35, then it redirects to the address in the set that has element just less than 35, okay, sorry, equal to 35, equal to 35. If there is nothing like equal to 35, it will point out to that element that is just greater than 35. All right. So S dot lower bound of 35 means that this will redirect to that address of that element that is equal to 35. If there is no 35 in the set, then it will redirect to that element that is just greater than 35. What does upper bound do? S dot upper bound of 35. What does this do? This will redirect to the element that is just greater than 35. This functionality is only to find the element that is just greater than 35. So let us see that. Uh, Auto IT1. So we are first getting the addresses. Lower bound and upper bound deals with address. So S dot lower bound of 35, because there is no 35 in our set. So we'll do this. And auto IT2. S dot lower bound upper bound. Okay, this time upper bound of 35. Okay, so IT1 must point to the address of 50, because 35, there is no 35 in our settings. So it will redirect to that address which is of that element which is just greater than 35. In our set, which the element that's just greater than 35 is 50. Same is the case with upper bound. It goes to the element that is just greater than 35. That is 50 again. Also, I'll do auto I3, IT3 as S dot lower bound of 30. Okay, because we have 30, we'll see what does IT3 does. And auto IT4 to be S dot upper bound of uh, upper bound of 30 again. Okay, and because I've told upper bound redirects to the element that is greater than 30, that's greater than the element that you're mentioning here. That job of upper bound is only that. And lower bound will get to that element if it is there. If it is not there in the set, it will go to the element that is just above it, that is just greater than that. So let us see out. So star is important. Okay, star IT1. So star, these are addresses. IT1, IT2, IT3 are addresses. So star denotes the value that is present at that address. So I'll be just copying it for 4 times. Uh, okay, there's a gap in between. IT2, uh, gap in between as well. Again, IT3. Uh, I'll just move this side. And okay, IT4. So we'll just run this program. I don't think there's any flaw in the code. So yeah, let's run this program. It's taking some time. I think it has lost the connection with the server. So let us copy this code and refresh the page. And I'll just remove this and I'll put it and I'll run it now. Okay, there is some mistake that we have done. Yeah. So this part, and in this part, even here I have not kept the space. Okay, star IT1, star IT2. star IP3, and yeah, everything's fine now. So let us run the program. Yeah, so not there. 5 set s sort size is 5 because we have inserted 5 elements 5, 10, 30, 50, and 70. And now you can see IT1 s dot lower bound of 35 because 35 is not there, it will point out to the 50. S dot upper bound of 35, it will point out to 50. Upper bound does that. And S dot lower bound of 30 because 30 is there, it will redirect to that itself 30. S dot lower bound of 30, upper bound of 30, upper bound as it points to that element that is just greater than 30, 50. So we have got those elements. I hope you understood what is the significance of lower bound and upper bound. If there is no greater than element than the element that we have kept in, let us assume we have kept the element that we are trying to find as lower bound of 75. Okay, lower bound of 75. There is no greater than element to 75, and there is no element like 75 not set. Then it will give s dot end. All right. So s dot end is what it will be giving us. So this is the lower bound and upper bound of set. So there's another version of this unordered set. The only difference in an unordered set and a set is it does not maintain this. Okay, it does not maintain the increasing order. It will be in a random order. It does not maintain any increasing order, and it does not maintain duplicate. That is for sure. The set is known for does not maintain not maintaining any duplicates, and in a normal set we have the main increasing order, and in an unordered set as the name says unordered, so you don't find any order in the set. Okay, so I haven't mentioned all the STL related to it in the document. You can go through it, and we are only left with maps, and we'll see that right now. Now coming to the concepts of maps. Okay, maps. So maps, as the English word says, maps. So you're trying to map something to something. Okay. So you're trying to map something to something. So for example, A, B, C, D, E, F, G, so on till Z. Okay. And we are actually numbering them from 1, 2, 3, 4, so on till 26. Right. So I can say that A is mapped to 1, B is mapped to 2, C is mapped to 3, so on. Z is mapped to 26. So if I say that I want the number that is connected to G, so I'll have a data structure which stores the number corresponding to the value of G. All right. So I let us take some data structure, and that data structure has the facility that if you provide the alphabet, then it would give you the number that you have stored corresponding to it. So that is where we can use maps. This is a very naive example. Like you can use various other examples as well. So for example, you have a basket and you have a lot of fruits in it: apples, bananas, oranges, right, etc., mangoes. It goes on. Okay, so now you need a data structure which can store the count of each fruit. So if I have some data structure which can store the count of apples, the count of bananas, the count of oranges, the count of mangoes, the count of grapes, etc. All right. So your data structure which facilitates this is a map. So your map has the feature of mapping one thing, apple, to its number of count. Okay, number or count. Okay, banana to its count, oranges to its count. So you're trying to map one thing to another thing. So this is where your map works. Okay, map facilitates this. So let us take the data structure. So this is how we define a map. Map int MP. Okay, I'm naming my map to be MP. So what does this int comma int mean? So map int comma int MP. So this says that you're mapping an integer to an integer. So what does this mean? You are mapping an integer to an integer. All right. So this is what it means. And what is your map name? MP. Okay, that's it. So if you are trying to map a string to int, then your map would be map string nt, and you can name it to be MP or something. It's up to you. You can name anything. Okay, so this is how a map works. So let us try it. So map int comma int MP. Now how can I try to link something to something? So if let us take this example itself, a b c d f g till z, let us take this example itself. So if that is the case, this must be a car, because these are all characteristics, right? These are all characteristics, and we are trying to map this character to a number. So map char int mp. So what will I do now? Mp dot insert of a1. So what does this mean? Insert. So now we have come across a new STL insert. So what does that mean? You're trying to put a pair. Okay. So it's not the pair that we have seen. It's different. We are trying to insert a pair x comma y into the map mp such that you are mapping x to y. So mapping x to y in the sense mp of x must be equal to that value. So whatever the x corresponding to that x you're storing, that will be available in the mp of x. All right, mp of x stores the corresponding value that you're trying to store. So now mp dot insert of a comma 1 means that mp of a equals to 1. All right, your map stores the value that you're trying to store to the corresponding character, that is a. To corresponding character a, I'm trying to store the value 1, and that will be stored in the map. So map dot insert a comma b. I even do mp insert c b comma 2. All right, so let us see out. So see out mp of a and space mp of b end. So let us see what would be a output. I actually did a small mistake over here, because we are actually storing a character and an end. We must put it under apostrophe. So this, and even in this case, and even here as well, and here as well. All right. So now let us try to run this program, and we could see that we got the values as 1 and 2, because corresponding to A we have stored 1, corresponding to B we have stored 2. So what is the other way that we can store an element? So mp of C equal to 3, you can directly put it, insert in this fashion, without using the command insert. Okay, without using the command insert, you can directly put this in this fashion. So mp of D equal to 4. All right, and now let us see what would be their value. See out mp slash mp of C and space, and then mp of D end. All right, so let us see this now. uh, yeah, sorry, I missed this. Okay, now let us see this. So we should get 1 2 3 4. Yeah, 1 2 3 4. Fine. So because 2c I've associated the value 3, 2d I've associated the value as 4. Now it's also important to see the size. Okay, so how do you find the size? Just see out mp dot size. All right, mp dot size, and then even after this, see out mp dot size end. All right, so at the first instance there are only two that we have inserted, so the size must be 2 in this case, and here we have associated two more values, that is C and D. So the size must be updated to 4. So let us see this. So 1 2, the initial size is 2, and then we have got 3 4, and then we have got 4. An important character of a map is, if you try to, right, if you even try to access any value that is not there, right? For example, let me try to get the output of np of E, right? Np of E. I have not associated any value of E, I have not inserted any value of E, but I'm trying to access it. So it would show me the result as 0. Okay, the result as 0. And similarly, it will also increase the size. So let us see the size now. Mp dot size ended. Okay. So now mp of E would be 0, and the size will be updated to 5. So let us check that. So 0 and 5. So it's very, very important. So as soon as you try to, try to explore something in the map, 2 it doesn't exist. So as you thought of exploring it, as you write it, the compiler will make the map update its size accordingly. Because I've tried to search for E, 2 it's not there, so it's showing me the answer as 0. The map corresponding to the E is showing me 0 because I'm not associated any sort of value to E. I'm not updated any value of E to the map. And the size also got updated to 5. The size has got increased by 1. Alright, so this is a very, very important characteristic in a map. So this is just about map char int. You can even store long, and int, not a problem. You can store anything corresponding to anything. Okay, you can use map string int, you can use map char string, anything. You can try to map anything to anything, not a problem. All right, so this works. And an important characteristic of a map is, I forgot to add that, it sorts in the ascending order. Like, I mean, it shows the values, like it stores, that is best, it stores in an increasing order. All right, it stores in an increasing order. So very, very important characteristic, like same as the set. Map also stores the elements in an increasing order. So this is a very, very important function of a map. And there are another two things that are there: unordered map and multi-map. All right, unordered map and multi-map. The only difference in unordered map is there will be no storage of the elements of the data in an increasing order. Fine. The same thing that we have seen the difference in set and unordered set. The same thing in map and an unordered map. The only difference is you will not be seeing the elements sorted in an increasing order. It will be a random. Okay, it will be random. And in multi-map, you can store the same value. You can use the same key for different sort of values. Okay, you can use, like for A, we are storing 1. In multi-map, you can use this A to store a lot of values. Your same key will be having a lot of values. Okay. Here it's like a one-to-one function. Your A is only mapped to 1. B is only mapped to 2. But in a multi-map, you can associate to a single key lot of values. All right. So I'm leaving this task, these as some tasks to you. So what are the things that I've left as a task to you for you to go through and study? So first one I've left is DQ. Okay, DQ. Second one I've left is unordered set. So I've explained almost everything related to unordered set. Just you just need to go through the other stuff. Okay, multi-set, and here in maps, unordered maps, and multi-maps. Okay, these are the things that I'm leaving as a task to you people to go through. Like I'm giving you, I've already provided you the document. All right, so in the doc version where you have all the links to this, just go through the links that are there. Just go through articles that are given in the links. Just understand what is there and that, how do we use it, the functionality, how do we iterate through them, do we really need them, come to try to come to some conclusion. All right, these are not much of in usage. And DQ, multi-set, multi-maps, very rarely we use. Unordered set and ordered maps, we use them in terms of like when there is an issue with the time complexity or something, then is the case we use them. All right, so yeah, so you need to go through those articles. That is what all I expect from you people. And we have covered a lot about map. And in map also there are something like lower bound and upper bound. So I'm leaving that as also a task to you. Like in the document, I've issued all the links for everything that I'm leaving as a task. I've given you the links. You just need to go through them, understand, because I've given you all the base that you needed to understand the concepts. That's more than enough, to be honest. I've given you all the base. You need to do some task work so that you can try to understand how do we learn things, right? So that is my main intention. And yeah, so the other part that we are just left over is math. Okay, so some of the STL like POW to take the power of two elements. So for example, int a equal to 2 and p equal to 3. So if I just see out power of 2, 3 and then, so what would I get? 2 cube, that is 8. Let's take a lot of, yeah, 2 power 3, 8. So power is actually used to take the power of one element raised to another. Okay. So for example, power of 2, 3 is equal to 2 cube is equal to 8. Okay. So this is how it works. And there is another work, another STL, that is GCD. GCD is greatest common factor. So this is how you write. It's like dash dash and GCD. Uh, so GCD of can be represented as dash dash. All right, GCD of AB. So you'll be getting the value that is HCF. Okay, highest common factor of A and B is what you'll be getting. It's taking a lot of time to compile. I'm having some issues with internet, so that may be the reason. So this is it for GCD, and you have another property like built-in popcorn something that I've mentioned in the document. Not very necessary, very rarely we use, and we have next permutation. All right, next permutation. This is a very important concept. So I would like to mention that yeah, got the internet back. Let us see now. So GCD of 2 3, yeah, okay. Next permutation. So next permutation gives you the output of all the permutations possible. So for example, if you take the string 1 2 3, all right. So the permutations would be 1 3 2, first 1 2 3, and then 1 3 2, and then 2 1 3, and then 2 3 1, and then 3 1 2, and then 3 2 1. All right, these are the permutations, right? These are the permutations. So next permutation give you all the sort of permutations that are possible. Next permutation, important thing that you note here is it goes on in an increasing value. All right, it doesn't first you give you the permutation output as 321 and then 312. This is not the way that it does. It will go in an increasing order. For example, now I've given 123, so I'll be getting the output as 6. If you give the input as 231, you'll be getting the output as 231, 312, and 320. All right, so only these three you'll be getting because it goes on an increasing order. From here, what are the increasing order possible permutations that will only you consider. So it's very important for you people to note this. And fourth one is max element, min element. So let us take a vector. All right. So vector int vec equals to 12, 40, 54, 23, 65, 78, 101, 123, 54. Okay, 23 I've taken, 29, 82. All right. So this is the vector. Now, if I see out star max element of vec dot begin and vec dot end. So what does this actually mean? So and L. All right. So star max element. So I'll just star max element vec dot begin and vec dot end. This is what we have written, right? So we'll understand what does it mean and clear. So star max element, star in the sense, so when you see a star, you must understand that it is being used to an address. So star is often used with an address. All right. So this gives you an address. All right. This gives you an address. But it gives an address to what? It gives an address to the maximum element that is present in the vector vec. Okay, our vector name is vec. So in that vec, what is the maximum element there? To that place, this address is stored. Okay, that place address is stored in this. And star, make sure you are pointing to the value that is present in that address. All right. So vec dot begin in the sense this is a starting element address that is 12. Vec dot end. So vec dot end is this after 82. What do you have? After 82, what you have that. So it is like an open bracket, close bracket thing. So it goes on. Sorry. Close bracket, open bracket. All right. So it includes this address, but it doesn't include this address. All right. So it goes on till the address that is next to the last element of vec, that is after 82. So it goes on searching here, and it will max element will get that address where you have the maximum element. So star max element will point out to 101 because 101 is the maximum element possible. So max element will have the address of 101. Star max element will have the value 101 because star indicates the value that is present in the address. All right. So that is very important. So this is of this related to max element. So what if we consider the same thing for min element? Okay. See out min element. Min element. So min element, what is the minimum element possible here? 12. So it goes to the starting. So let us run this. So we must get the values as 101 and 12. So 101 and 12. I hope you understand. So this is a very important STL. Like if someone asks you to find the maximum element and minimum element, you can just give this directly. All right. So yeah, this is very important. And many don't teach you this minimum and maximum of two or more than two elements, two or maybe three or more than three elements. Okay, more than three elements. So many don't know this. So what is that is, so for example, if you have two integers, 2 b equal to 3. Okay, b equal to 3. Now if I say that C out minimum of AB, it's very easy, right? And then, all right. So what if, okay, let us run this first. So minimum of AB, we'll be getting the answer as 2. 2. Now, what if there is an extra element C3? What would people generally do is they will take a minimum again, minimum of B, comma C, and then they'll write it. So this is how they do A, comma minimum of BC. So this is how you'll be getting the final value to be 2 anyways. And if there is an extra element D equal to 4, so what would they do? Then again, write minimum of a comma d, and then try the minimum of this and minimum of this, and from that two minimums take the minimum. So this is how they'll do. Like this is like writing nested of nested of nested. So instead of this, we can directly write in this fashion. So take curly brackets and put a b c d. It's your choice. Like if there are 26 elements, put 26 elements in the curly brackets. No need of mentioning min of min. So instead of that, you can just directly do this. So if you run this, you would get the answer to be 2. It's taking some time. Yeah, so 2. So same is the case with max as well. CO max. So let us do this. So you'll be getting the answer to be 4. Uh, 4, right? So this is how it works. So instead of doing all the stuff, you can just put minimum curly brackets, maximum curly brackets. All right. So very few people know. Very few people know. So this is a value addition. This is definitely a value addition. Like this can actually help you write your code much faster. All right. So I hope you understood all these things. And yeah, we have covered a lot of things, to be honest, related to STL. We have divided them into various data structures, and we have tried to cover all of them. I don't think I left anything, but still, if I left, I've covered all of them in the document. So just go to the document, go to the article, click the article, will be redirected to GFG site. Read everything about that particular STL. If you don't understand anything, feel free to DM me. I'll always be there. And also, please don't forget to submit your feedback. All right. Uh, Submit your feedback. This is very, very important for me. All right. So submit your feedback as well as go through the notes. Go through the notes, documents as well as notes. Like this is also this slide also I'll be sharing the where I've annotated. I'll even share this, so it will be helpful for you to revise. So this is all for the very first lecture. In the next lecture, we may try to cover some algorithms, or we may start with binary search or something. I don't know. Like, but yeah, we will definitely step into a next type of sector in this course. And yeah, thank you so much, guys. You have spent a lot of time. I hope you'll actually go through the things that I've said. And yeah, it's very, very important for you people to be consistent down the line. And it might feel hard for you people right now, but as you go further, it will be a cakewalk for you people to, go through the data structures and all. Like I've kept it as simple as possible. And yeah, so thanks for the trust that you had in me and spent a lot of time till this point. If you have come, that means you have done a really great job. So yeah, thank you again, and we'll see you in the next class.